today we want to be able to finish off chapter 22. Um, that's going to be our goal. I will point out that the second exam covers chapters 21 or 20, 21, and 22. So yeah, we're just now doing exam 1, and exam 2 is coming up next week. So yay, rapid fire. Hooray. Um, so the thing that we need to finish up with chapter 22 is a couple of things. Um, One of them is we want to put the stuff we did yesterday and kind of combine it with the stuff we did the day before yesterday. We want to basically deal with the force between two parallel wires, and to do that requires that we know all the stuff we've done for the last 2 days. So let's think that through. Your book covers this in the very last section of the chapter. Um, so imagine I have two wires that run parallel to one another. So here's a wire, and here's another long wire. And let's assume that both of these wires have current traveling in the same direction. So I1 is current traveling through this wire downward. And in this wire, I have a second amount of current, which may or may not be the same, also traveling downward. Now, what's going to happen is, because the first wire has current traveling through it, it's going to produce a magnetic field everywhere. And because magnetic fields generate forces on moving charges, and wire 2 is full of current, which is moving charges, then the magnetic field of wire number 1 is going to induce a force on wire number 2. And of course, Newton's third law says that the reverse will also be true. Wire number 2 is producing a magnetic field. Its magnetic field will produce a force on wire number 1. So each of these two wires is going to produce a force on the other one. And in order for us to figure out what that force is going to look like, let's start by figuring out the magnetic field created by wire 1. Now, we did that the other day using Ampere's law. And again, just to review how that works, what you do is you pick a path that encircles your wire in some way. It has to go around your current in some way, and it has to obey two rules. Rule number 1 is that I always want to have my path that I choose follow the magnetic field wherever possible. And where I can't follow the magnetic field, I want to go perpendicular to it. And that's because the Ampere's law expression has B dotted to your little path, delta L. And because it's a dot product, you do dot products by taking the magnitude of the first thing times the magnitude of the second thing times the cosine of the angle between them. So that would be B times whatever dl is times the cosine of theta. This is Ampere's law we learned yesterday. And what's going to happen is, if we're always moving along a path that is in the same direction as B, the angle between those two things is always going to be 0, and the cosine of 0 is always going to be 1. That makes it super simple. If we can't do that, but instead during that portion of the path we go perpendicular to B, well, the cosine of theta in that case is going to be the cosine of 90, which is 0, and the whole thing just zeroes out. So the idea is that as we go around that path and we're adding up all these little b's times tiny lengths, because technically this is like a big sum. I'm going out of my way to avoid writing integrals. But as long as we're adding up all those little tiny contributions around the path, if this is always either 1 or 0, it makes it super easy to calculate. If we picked some path that was more complicated, where the angle between the magnetic field and the direction we were traveling was some kind of weird, complicated angle, then it would be way harder to calculate. We just can't do it. So we're doing this to make it super simple. So we always want to go with the magnetic field where possible. And the second rule is because we want to be able to just multiply one number for B times one number for my length, what we want to do is pick a path where everywhere on that path that the angle between B and L is 0, we want to make sure that B has the same value the whole time, that it's one uniform number. And usually you can make that argument from symmetry. So for instance, if I'm thinking about wire number 1, if I go 1 meter to the left of wire number 1, I'm going to get a certain size magnetic field. But if I go 1 meter to the right of wire number 1, there's no reason why the magnetic field on its left side ought to be stronger than the magnetic field on its right side. And so since I'm the same distance on either side, whatever the magnetic field is, I ought to be able to make the argument that it should be the same in both places. And in fact, if I'm always the same distance away from the wire as I go around it, there's no reason why B should be stronger in one place than it is in some other place. So from symmetry, if I'm going around a path that is concentric to the wire, then everywhere along that path B is uniform, and Ampere's law should work for us. So what Ampere's law says is that if I take the size of B times the distance that I'm traveling around that path times the cosine of the angle, which we've picked it such that this is going to equal 1, it's going to equal mu naught times however much current is enclosed by the loop. And in this particular case, what's going to happen is the distance around the path is the distance around a big circle, which is 2 pi r. And the amount of current that is enclosed by this loop is whatever I1 is. So the magnetic field created by wire number 1 would be given by this. So I'm going to call this B1 since we're talking about wire 1 specifically. And again, this is generally going to be true for any long straight wire. It's super helpful. Now, what the heck is R? R is the distance between the wire and wherever the path was that we picked. And if I had picked a bigger path, I would have had a bigger R and therefore a weaker magnetic field. So I can put R and make R be whatever distance I want it to be. It's however far from the wire I choose to get. Well, I'm particularly interested in the magnetic field that's caused by wire 1 at the location of wire 2. So I'm going to call this distance D. That's the separation between the two wires. And I'm going to evaluate the magnetic field of wire 1 at that location. All I got to do is make R be the same as D. So this is the magnetic field at the location of wire 2. Nifty. So now that I know how big the magnetic field is that wire 1 is causing at the location of wire number 2, now what I want to do is figure out what force that is going to generate on wire number 2. And for that, I'm going to use the Lorentz force law. That's how you find the force from a magnetic field. Now remember, the Lorentz force law has two different forms. There's the one form that we learned first that was QV cross B. And this would be generally helpful if I have individual point charges flying around, but it's not helpful when I have wires. So we're not going to use this version. The other version that we learned was for wires, and that's going to be way more helpful. And that's that the force equals the current times the length of the wire crossed with B. And it's going to work the same way. Now, in this case, we want to find the force that this guy feels. And his force is going to depend on however much current runs through him. So the I in this case is going to be whatever I2 is. The length in this case is going to be whatever the length of that wire is. I'll call that length 2. But the magnetic field is the magnetic field that's being caused by wire 1. And of course, when you're doing a cross product, you'll take the magnitude of L times the magnitude of B times the sine of the angle between L and B. And what the heck's the direction of the length? Well, the length vector points the same direction as the current. So in this case, it's downward, right? So we should probably figure out what the angle is between the L vector, which points downward, and the magnetic field that this guy creates, because we didn't do that yet. So remember how to find the direction of the magnetic field, right? We know the magnitude of the field is this, but it doesn't tell us what direction it points. To get that, what we're going to do is a version of the right-hand rule. We're going to take our right hands, and it's important you use your right hand. And for a long straight wire, the trick is take your thumb and stick your thumb in the direction of the current. So the current is downward. I'm going to stick my thumb downward. And what's going to happen is my fingers are going to wrap around the wire in the direction of the magnetic field. So in this case, the current points downwards. So my fingers are wrapping around sort of over the top. But that means that on this side of the wire, the current is into the page. On the other side of the wire, my fingers are going to be curling up. So that tells me that when I'm over here, the magnetic field from wire number 1 points out of the page. So what's the angle between L and B? Well, the current is downward, the magnetic field's out of the page. That's a right angle. So the sine of 90 is conveniently just 1. So all I have to do to evaluate that force is just replace B with that expression. And what I'm going to end up with is I'll have mu naught times I1 times I2. So it's going to depend on the products of my two currents times L2, the length of the thing, and it's going to be divided by 2 pi times the distance between them. So notice, the longer that second wire is, the more little bits of it there are to feel forces, and that adds up, and that's why the force gets bigger depending on the length. The further apart they are, well, the bigger the D is in this expression, the smaller the force will be. That makes some sense. And of course, the larger I make the currents, the bigger the force. So I can crank those currents up to whatever I'd like them to be. So this gives me the magnitude of the force. What it fails to tell me is the direction of that force. So let's think that part through as well. So to find the direction of a force, we have to use this cross product, which means using the right-hand rule. And we're crossing L and B. And L comes first, so we have to take our right hand and put our right hand so that our fingers are in the same direction as the current. And I'm going to do something because I hate having to wrap my fingers around like this. It twists my hand. Watch this. I'm flipping that around. There we go. So now it's easier for me to put my fingers in the direction of the current. I'm being lazy. So here's the current. My fingers are pointing in the direction of the current. The magnetic field, however, points out of the page. So what I'm going to do is I've got to bend my fingers out of the page, which as I'm holding it right now is not going to work because I'm not some kind of double jointed freak. Instead, I got to rotate my hand. Notice my fingers are still in the direction of L, but now I can bend my fingers in the direction of B, and my thumb will point in the direction of the force. So you can see that in this case, wire number 1 is being pulled, or sorry, wire number 2 is being pulled towards wire number 1. So now I can flip that around, and I know that the force is going to be that way. And of course, from Newton's third law, I already know that if wire 1 is pulling wire 2 towards it, then wire 2 ought to be pulling wire 1 towards it. So I could do that. I could also do the reverse of the same argument, right? Because this guy here creates a magnetic field. Using the right-hand rule, it would point into the board over here. So now if this guy points downward and the other guy is into the board, the right-hand rule would give me a force to the right. So I can do it the hard way as well, and I would get a similar amount of agreement with experiment. So it turns out that for two parallel wires, when I have the current traveling in the same direction in each wire, the two wires end up attracting one another. Neat. What would happen if I were to reverse the direction of one of the currents? What would happen if I took wire 2 and flipped it so that the current was upward instead? Well, now what would happen is wire number 1 is still creating the same magnetic field it always was. So the magnetic field here hasn't changed. The strength of it hasn't changed. When I do this, the sine of theta is still 90. The size of the force wouldn't change, but the direction would, because now I take my current, flip it up. Now it would be repulsive. So a quick and dirty way to remember this is that when the current is in opposite directions in my two wires, they'll always repel. And that sort of magnetic repulsion is something that's actually kind of useful. One of the ways that we generate like magnetic levitation trains, like the kinds you have in Japan, is, you have current flowing in wires and you have large magnets, and what's going to happen is those wires are repelled by that magnetic field, and if that repulsive force is strong enough, you can cause the entire object to hover above the ground and therefore avoid things like friction. So pretty neat. All right, so hopefully there's no questions with that. That's pretty straightforward, I think. One thing I will point out is that in many cases, when we're doing this Ampere's law expression, technically this only works if I can make the argument from symmetry that the magnetic field is the same everywhere along that. And that only technically works if this wire is so long that it might as well go on forever. But if the wire is infinitely long, then what the heck do I put in for L2, right? The length is going to be super, super long, right? And so since this expression is typically derived specifically for infinitely long wires, we often write it a slightly different way. If I just divide both sides by L, and I'm going to drop the subscript because I could always replace L1 and L2 because they're both the same. Very frequently, we'll express it not in terms of the total amount of force that they feel, but the force per length. The idea is that each section of the wire feels a certain amount of force, and that's what F over L would be. So don't be alarmed if you see a question ask you, I think one of your homeworks does, for the force per length rather than the force itself. So there, you would just be doing this, because the force per length would be whatever that is. And you wouldn't necessarily need to know the total force, nor would you need to know the total length. You could just find the ratio given by that. And that's a common way to pose that problem. So in terms of sort of things we haven't seen in the chapter that are calculational in nature, that's pretty much the end of it. There is one more little thing that we should probably talk about, and it's one of those things that I'm always surprised, because we end up going through pretty much the entirety of chapter 22, talking about magnetic fields and magnetism. And we're always talking about charges moving around or current in wires. And I always expect one of my students to stop me and say, wait a minute, when I think about magnets, I'm thinking about the things that stick to my fridge. And there's no electricity, there's no current in those stupid things. So what the heck does all this garbage we've been talking about have to do with the stuff that sticks on your refrigerator? Like, how on earth is that connected to any of this stuff? Because it's not obvious. And in fact, we actually end up not doing a whole lot of work on that just because it's hard to quantify at this level. But we can at least give you a sense of where that connection is, and hopefully a better sense of what's happening to those things on your refrigerator and how they're playing out. In order to do that, though, I need to think about what's happening inside a permanent magnet on a microscopic level. So let's do this. Let's picture that I've got some kind of object, right? And every object is made out of atoms. So here's a bunch of atoms. Obviously, this is not to scale. Now, if this object is a permanent magnet, you might ask yourself, how on earth am I going to get, a permanent magnet to generate a magnetic field if magnetic fields require charges to be moving around? Like, where's the moving charge? There's no battery connected to this permanent magnet. There's no electricity flowing through it. So why should it be creating a magnetic field the same way a wire would if there's no current? And in order to make sense of that, you've got to think about what's happening on each of your atoms. Because what is an atom, right? It's a positive nucleus with a cloud of electrons that buzz around them. Oh, wait. Electrons are buzzing around them. Those electrons are moving. They're moving around your atom. And of course, we think of them, when we first learn about like atoms and chemistry in usually GChem, the first way we model an atom is with the Bohr model of the atom, where you literally have, here's a little positive nucleus and here's a little negative electron, and that negative electron is literally orbiting kind of like a planet. And electrons with higher energies are literally orbiting with bigger radii. And I will point out, just for the sake of accuracy, that this picture is not really how it works. It's kind of a cartoony first sort of guess at how it works, but the real answer is way, way weirder and way more complicated. But it'll work for our description right now. It'll help us understand it. But the idea is that if these little electrons are charged particles and they're traveling in orbits around this atom, you've got charges and they're moving. So that in a way creates a sort of current. And that means that every electron around every atom in every object ever creates a magnetic field. Every electron. And there's electrons in everything. But then that begs the question, if every atom has electrons and every electron is moving, then, and therefore every electron creates a little tiny magnetic field, why doesn't everything stick to my refrigerator, right? Why don't all atoms create magnetic fields that can become permanent magnets? What is it that's special about these certain materials that make them magnetic and other materials non-magnetic? I mean, if they've all got electrons and all the electrons are moving, they're all creating magnetic fields, why doesn't my pen stick to a magnet? Well, it has to do with the fact that in an atom, you've got a whole bunch of electrons, but they're not all buzzing around the same direction. So think about it this way. If I think of this sort of simple electron, or this simple model here, imagine each of these guys are buzzing around clockwise. So if they're buzzing around clockwise, they're going to create a magnetic field the same way that the current in a loop would create a magnetic field. And if you're buzzing around clockwise, you take your right hand, curl your right hand in the direction of the motion, your thumb's going to point in the direction of the magnetic field. So this little electron here and this little electron here going around clockwise would make a magnetic field that points into the page. But what's going to happen is you've got a gazillion atoms in your material, and maybe the electrons on this atom are buzzing around clockwise, making a magnetic field pointing into the page. But maybe the guy next door, they're buzzing around clockwise, making a magnetic field out of the page. Maybe the guys over here, they're buzzing around kind of out of the plane of the board, and they're making a magnetic field that points to the right. So what's going to happen is each one of these atoms might create a magnetic field in some random direction. And so even though there's a magnetic field created by each individual little atom and each individual electron in each atom, for most materials, what's going to happen is all those magnetic fields are just sort of randomly arrayed, and they're just as likely to average out to nothing. And so that's the idea, is that most materials, you've got random, what they call magnetic moments, and they all tend to cancel out. And that's why you get most materials that don't have some net magnetism. Right? It's why my pen doesn't stick to magnets, is because the magnetic moments of all the electrons just tend to be sort of random. Something else I'll point out is that there's two different ways you can get these magnetic moments, right? I've drawn one, and that's from the orbital motion of each of these little electrons. Each electron going around the nucleus has orbital motion that creates a magnetic field. But you also learn about electron spin in GChem, right? We say that each electron has spin, either spin up or spin down. And you can kind of think of spin in this sort of inaccurate but cartoony way as, imagine like you've got planets, like planets go around the sun, but they also spin on their axis. And so that creates a magnetic field as well, the fact that these electrons are doing their spin thing. And what's going to happen is the magnetic field created by the orbital motion is actually not nearly as big as the magnetic field created by the electron's spin, or what we call the intrinsic magnetic moment of your electron. So we're going to pay most of our attention thinking about the spin of my electrons. But that creates some complications, because if you recall from chemistry, there was something called the Pauli exclusion principle. Right? And the Pauli exclusion principle said that no two electrons could exist in the same quantum state. And that had a lot of implications for chemistry when you were thinking about the electronic configuration of your electron orbitals. Because what it meant is that you couldn't have two electrons be in the same orbit and have the same spin at the same time. And that led to all kinds of electronic configuration stuff. Like, remember, if you did the electronic configuration of a helium atom, helium is number 2 on the periodic table. And so it has 2 electrons. But what's going to happen is those 2 electrons both occupy the lowest energy state, which in that case was what we called the 1s level, right? And so we would say that helium had an electronic configuration of 1s with 2 electrons. It's not a squared, it's just 2 electrons. That's how chemists write it. So what that means is that you have 2 electrons in that lowest orbital. But if I go up to the next atom on the periodic table, which is lithium, lithium has 3 electrons. And what's going to happen is it's going to have 2 electrons in that 1s2 state. But the problem is I can't put a third electron in that 1s2 state. And the reason is because in the 1s level, I have 1 spin up and 1 spin down electron, but you can only have 2 electrons in that orbital, because if I put a third one in there, it would either be spin up or spin down. You can't have 2 of the same in the same orbit because of the Pauli exclusion principle. So what happens is that next electron, the one for the lithium, you'd fill up the 1s level, and then you'd have the 2s level, the higher energy orbit further out here, and that third electron would have to go into that orbit. So hopefully this all seems familiar to you from back in the day when you took general chemistry, because you spent a lot of time talking about this. But all this is that, you've got electrons and they each have spins, which each creates their own little magnetic moment. And you can't have more than one spin of a particular kind in an orbit. So sometimes you got to kick guys up into higher energy levels. Now, here's why that makes a big deal when it comes to the magnetic field created by most materials, right? Electrons tend to form little pairs, right? Well, a spin up and a spin down. Well, what's going to happen is if I've got a level where I've got a spin up and a spin down, then what that tells me is that they're both in the same orbital, so they both have the same orbital magnetic field. And on top of that, one of them is spin up, the other one is spin down. They're going to make a magnetic field for their spins that are both equal and opposite. So having paired up electrons, their magnetic fields are going to cancel each other out anyway. So the vast majority of the electrons in any material are going to be paired up. Their magnetic fields are going to cancel out anyway. And it's only those materials that have a lot of unpaired electrons that you would expect to make a net magnetic field anyway, right? Having all paired up electrons means you're probably going to be non-magnetic. Having some unpaired electrons could open the possibility, but not the certainty, that they might be good magnetic materials. Now, in order for them to be a good magnetic material, it's not enough to just have some unpaired electrons like lithium, because lithium is non-magnetic. It's also important that all those unpaired electrons tend to line up with each other. And so if you have a permanent magnet, what's going to happen is you've got a bunch of atoms and on those atoms, what's going to happen is you've got maybe some unpaired spins. So here's an unpaired spin on this atom. He's creating a little tiny magnetic field. Now, the magnetic field created by this atom here will influence the electrons on the adjacent nearest neighbor atoms. And for most materials, what's going to happen is the interactions between the electron spins on this atom and the electron spins on the atom next door are so wimpy that they don't really cause much influence. And as a consequence, on most materials, even if the spins of this guy line up one direction, the spins on the other guy might be the other direction. And overall, they tend to average out to zero. So even if you've got unpaired spins, you probably still aren't a very good magnet. However, in some materials, they're configured in just the right way that the magnetic field created by one atom tends to exert a force on the spins on the adjacent atom, and so they tend to enjoy lining up together. And if that's the case, if you get all the spins that are unpaired on various atoms lining up over some large region, they're not going to cancel out. They're going to add up. And you'll get what we call magnetization, right? This thing will become magnetically active. And that's the kind of stuff that's sticking to your fridge. So that's what's happening. So it turns out that we can actually classify materials based on the nature of these nearest neighbor interactions. And there's some broad categories that I'd like you to be familiar with. The first is what we call a diamagnetic material. Now, a material that is diamagnetic is a material in which the spins, for whatever reason, can't line up together very easily at all. Usually it's because you've got a lot of paired up electrons so that if one is going the one way, the other is forced to go the other way. They can't line up together, and so they're always going to tend to cancel. And what that means is that since the vast majority of electrons in the vast majority of materials are paired up, most materials are diamagnetic. Almost everything is diamagnetic. In fact, let me take that qualification away and say everything is diamagnetic. What's going to happen is in the few things that aren't that are not diamagnetic, it's because they have diamagnetic tendencies that are sometimes overpowered by the fraction of electrons that are not diamagnetic. So everything is to at least some degree diamagnetic. And it's because everything's got paired electrons and they can't coexist together with the same spin. They always have to be spin up and spin down. And that means they can never be happy. So if I take a diamagnetic material and I immerse it in a magnetic field, in other words, here's my little diamagnet. And what's going to happen is I've got lots of spin ups and lots of spin downs. And I turn on an external magnetic field. Well, what's going to happen is this spin over here is already lined up with that magnetic field. It's like a compass needle lining up with the magnetic field of the Earth. It's happy. But this guy over here is about as unhappy as he could possibly be, right? He wants to turn around and line up with that magnetic field because the magnetic field's creating a torque that makes it want to rotate. But it can't, because if it lined up with the magnetic field, it would be violating the Pauli exclusion principle. So what's going to happen to this diamagnetic material, since it can't make all the electrons happy, is that this material will try to push the magnetic field away and out. So diamagnetic materials are always repelled by magnetic fields, period. And remember, I said that most everything is diamagnetic, which means almost everything is repelled by magnetic fields. And again, if you're paying attention, you're like, Tom, that's not how it works, because if you take your stupid plastic pen and you put your plastic pen next to a magnet where there's a magnetic field, nothing happens, right? So how can I get away with saying that everything is diamagnetic and therefore everything is repelled by magnetic fields when clearly that doesn't seem to be true? And turns out it totally is true. It's just that the size of that repulsion is very, very wimpy. It's wimpy enough you don't normally see it. So as you guys have certainly picked up, having taken my class for at least one semester, I'm a gigantic nerd, right? And as a gigantic nerd, I love me some comic books, especially Marvel comic books. And in Marvel Comics, you have the X-Men, and the X-Men's primary enemy, like the main bad guy for the X-Men, is Magneto. And if you've seen any of the X-Men movies, right, there's always a scene, right, where Wolverine, who's got this big metal endoskeleton, goes up to fight Magneto, and Magneto's like, you idiot. And he just freezes him solid because he's magnetic and he can control the metal inside Wolverine's exoskeleton. And suddenly Wolverine is out of that fight for the rest of the scene because he can't move. It's happened in like at least 3 movies. But wait a second. Magneto can make some crazy huge magnetic fields, and everything's diamagnetic. So technically, the comic book writers and the movie writers, they're getting Magneto wrong. If Magneto wanted to immobilize literally any of the X-Men, he could have done that just as easily as he does with Wolverine. And just to show you that I'm not making this up, all right, we're going to see if this works. Pull up visual evidence. So what we're looking at here, or we're about to be looking at, is a pretty crummy low resolution YouTube video of diamagnetism in action. So what these scientists in the Netherlands have done is they've got a large magnetic field, the kind of magnetic field you generate in an MRI. And they've then taken a tiny little frog and they put it inside this exceptionally large magnetic field. And so what you are witnessing is a little frog bobbing around somewhat randomly inside a magnetic field. Pretty crazy. It doesn't just work with frogs. I think this one is, oh, that's the frog. Where's the grasshopper?
Hi, Ameran.
All right, there's the guys doing this. So what you're seeing right here is they're pumping probably liquid nitrogen right now, maybe liquid helium. But they're using a supercooled gas to make their magnets, their electromagnets, super cold, so they do superconducting. And then they drop it into their chamber, and here's the frog floating again. By the end of this video, they'll do some other objects as well. Here's some kind of plant from the herb garden. It's floating too. Here's a guy speaking in some language I don't understand. Where's my grasshopper, dude? I came here for grasshoppers. All right. Here's somebody doing the same trick with a strawberry. So basically every object is at least a little bit diamagnetic. Now, what would it take for me to levitate a human? Well, the thing about the frog and the strawberry and the grasshopper is that all of those are pretty small, right? They all have a small mass, and that means that gravity is pulling them down with a very small amount of force. So in order to levitate them, all you had to do is generate the same size small force from the magnetic field. And that means that you could do that same levitation without a whole lot of magnetism, right? And even then, when I say not a whole lot, we're talking like probably 5 or 10 Tesla in those magnetic fields. Those are pretty big fields. You're not going to see those around. Now, a human is going to end up having a mass 1,000 or 2,000 times larger than that of that stupid frog. But if I'm going to have 1,000 or 2,000 times more mass, I'm going to need 1,000 or 2,000 times more magnetic field. And while I can generate a magnetic field of 10 Tesla in the lab easily enough, getting a magnetic field of 1,000 or 2,000 or 20,000 Tesla, that's over the top. So the reason you can't do this with people is we can't make magnetic fields big enough to make that observable. But it does happen. So for diamagnetic materials, they will be repelled very, very weakly by magnets. And most materials are at least a little bit diamagnetic. People, frogs, grasshoppers, they're diamagnetic. How will you know? They're repelled by fields. Super easy. There, do I have something playing in the background? I do. Stop playing in the background. All right. Now, there are other materials that we call paramagnetic. Now, a paramagnetic material is a material where you've got some unpaired electrons. So not every electron is paired up like this. You've got some unpaired electrons. And more importantly, when you turn on an external magnetic field, what's going to happen is, even though these guys may be randomly oriented most of the time, so like if something's paramagnetic, it won't normally seem like a magnet. But when you turn on a magnetic field, then what's going to happen is all those randomly oriented unpaired spins, they suddenly like can flip around and line up with the magnetic field. They can basically do this. And the reason they can get away with that is because this guy can be spin up and this guy can be spin up because they're on different atoms. They're in different orbitals. So they're not violating the exclusion principle by having the same spins. And so what happens is when I turn on that external magnetic field in a paramagnet, the atoms all try to line up, but now the material itself creates a magnetic field, and all of a sudden, whoop, they're going to stick. So paramagnetic materials, they're going to have unpaired spins that line up. In the presence of a magnetic field. So what's going to happen is, you know, these things would not normally exhibit a magnetic field, but you bring them close to a magnet, they'll stick to the magnet. You take the magnet away, and what happens is all these lined up spins, when you take the external field away, they tend to rattle around and they just end up going back to randomness. So you take the field away, they go back to randomly oriented spins and they're not magnetic anymore. Turn the external field on and they all line up and stick to the magnet. So paramagnetic materials would be attracted to magnets. So if you got a piece of metal which is not itself magnetic, but you stick it on a magnet or stick a magnet next to it and the magnet sticks, that material is paramagnetic. So like your refrigerator is paramagnetic, right? Because you know what's going to happen is it doesn't attract stuff by itself, but you put the refrigerator magnet next to it and the magnetic field of the refrigerator magnet causes that section of your refrigerator to become magnetized and the magnet can stick. You take the magnet away and suddenly the fridge doesn't stick to things anymore. It's only in the presence of the magnet does the fridge feel that attractive force. And it's because once you take that magnet away, these spins go back to being random again. Now, there is a special case of paramagnetism, and of course I wrote poorly. That is what we call ferromagnetism. And a ferromagnetic material is a special case of a paramagnetic material, right? Because what's going to happen is, just like a paramagnetic material, you may have spins that are randomly oriented every which way, and so there's often no net magnetic field for these things. However, what happens is you bring a ferromagnet next to an external field, all the spins line up just like a paramagnet. However, when you take the external field away, the interactions between atoms are sufficiently strong that once you take this field away, these guys are happy to stay lined up, right? When this guy tries to go back to being random, all the others around are like, no, 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 stay with us. And so a ferromagnet is what we think of as a permanent magnet. The things you're sticking on the fridge are ferromagnetic. You know, we call one of the canonical example of a ferromagnetic material is a piece of iron. Iron is a ferromagnet, right? And of course, like the prefix ferro, right? There's a reason iron on the periodic table is Fe, right? It's ferrous. So ferromagnetic literally means it's like iron. And so if you just take a random piece of iron, it doesn't stick to anything, right? Right. Most random pieces of iron, you put it next to another piece of iron and they don't do anything, right? Because normally their spins are all weird and random. However, if I take that piece of iron and I stick it in a large magnetic field, I can magnetize that piece of iron. And all of a sudden, it's going to stay magnetized. When I take the magnetic field away, the iron is still it's still created a permanent magnet of sorts, and now I can stick it to stuff. That's pretty cool. Now, ferromagnets are not truly permanent because it turns out that if you take a ferromagnet, you magnetize it so that all the spins are lined up nicely. But then you stick that ferromagnet in the oven and you get it hot enough. For every ferromagnet, there will be what they call a Curie temperature. And once you go above that Curie temperature, you're rattling around these atoms so much with heat that the spins break away and they go random again, and they can't go back on their own. So you can cause a permanent magnet to become demagnetized just by getting it hot enough. Try it. No, don't try this at home. Do not stick your fridge magnets in the oven. One, you may not be able to get to its Curie temperature. They may be quite high. And two, I don't want to know what chemicals you'll be releasing into the air if it burns. So let's not go there. But you could. A lot of my time in my research work has been studying some ferromagnets, but they have a Curie temperature that is exceptionally low. So things at room temperature may seem perfectly diamagnetic, except that, or at least paramagnetic. But when you cool it down below, say, 20 Kelvin, all of a sudden it's a ferromagnet. You can magnetize it and keep it that way. Pretty neat. So those are three classes of magnetic materials that I expect you guys to be familiar with. You should be able to identify what sort of material it is based on how it behaves. So these guys would be attracted to any kind of magnets, but two paramagnets, put them in a magnetic field, they're magnetized. Take the magnetic field away, they don't stick to each other anymore because they go non-magnetic again. Two ferromagnets, the same deal. You put them in a magnetic field, they'll magnetize, but then after you take the field away, they stay magnetized. And this guy over here, you put it in a magnetic field, it's going to push it away no matter what. North Pole, South Pole, I don't care. It doesn't want to be near it. Most of my work is with type 2 superconductors, which are an example of perfect diamagnetism, just because it's cool. I will show you some of that. So this is a superconductor. So shooting. On the surface. Right, with a regular camera, we can't see through the gap. I have no idea if you can see the audio on this over the internet connection.
But we are here to levitate an object, so what does liquid nitrogen have to do with magnetic levitation? Because you can make magnets levitate without it right now.
This guy's shirt made of pizza.
Levitating rings, which is a fun product that Michael, Kevin, and I made for the Curiosity Box.
All right, can we skip to the end of this video? All right, this guy's talking too much.
That they have zero electrical resistance, but more important for our purposes is the Meissner effect, which causes a superconductor to completely expel magnetic fields.
So that's perfect diamagnetism. The magnetic field is literally being ejected from the material. It can't get inside it, so it's being repelled by those magnets.
Even though the material itself is not magnetic. Now, this is our superconductor, a small disc made of yttrium, barium, copper oxide. Actually, in this whole thing, the superconducting material is just a tiny sliver of crystal thrown on top of a stainless steel core and covered by a protective layer of silver and aluminum. And when I say a tiny sliver, it really is. It's just 3 microns thick, 30 times smaller than the thickness of a human hair. And if I were to put a magnet next to it, well, nothing happens because it will only levitate when it's below that critical temperature, which is why I drowned it in liquid nitrogen.
So they're getting this thing super cold. YBCO has a critical temperature between as high as 90 Kelvin, sometimes as low as about 60 Kelvin. They're putting in liquid nitrogen, which is 77 Kelvin. So
not only does the disk hover above the track, but it can hover below it as well. In fact, we can shape the track any way we want, and the disk zooms along at exactly the same height, no matter its orientation, with no friction or resistance. That's due to a phenomenon called flux pinning or quantum locking. Basically, while the Meissner effect means that any superconductor will expel magnetic fields, if you intentionally introduce some imperfections into that material, then a little bit of the field can penetrate.
This, by the way, is what my dissertation was about.
Called flux tubes. Inside each of the tubes, essentially a tiny bit of magnetic field gets trapped inside the superconductor, pinning it in place. And what I mean by that is that our superconductor, our disk, is quantum locked to the magnetic field generated by this track. That's what allows our disk to go back and forth and upside down without falling off or flying off either end.
So I thought that would be pretty cool for you guys to see. So hopefully that shows up on the video. I don't know. All right, stop talking, dude. I'm done with you.
Now, to be entirely honest with you, I don't know how to end this episode. So here is some more.
Here's how you end it. I click off the video. All right, so in terms of stuff from chapter 22, that's the stuff that I expect you guys to know. Can you do anything quantitative with that? Not really. We're pretty well limited in how we handle that. All right, so I'm going to go ahead and end the session today here because we're about to start chapter 23. Chapter 23 is going to be an entirely new exam. It's going to be on exam 3, not exam 2. So we're looking at doing exam number 2 next week. So if you haven't already started doing some of those circuit problems or the magnetic field problem, you should definitely try to knock out as many of those as you can by the end of the weekend. I don't think we're not going to have the exam Monday. That's too soon. But Wednesday or Tuesday seems not unreasonable. So before I kill this, Tamisha, you're the only one who's logged in live. Got any homework questions that you want to deal with? Because we got time.
Not at the moment. I'm pretty straight with homework.
Okay. Yeah, one of the things that's happening is because we're doing this online, our pacing is like crazy fast anyway, and it's even faster than normal because in a regular class, at least 25% of our class time ends up being me fielding questions about homeworks during class. And because nobody's asking me questions about homeworks during class, we're not doing any of that. So,
okay.
So that's why things are progressing so quickly. So if you've got
Okay.
questions and you're here live, by all means, be ready to answer them because I can guarantee you, if you're not sure, there's somebody out there who's taking the class, but maybe not doing the in-person sessions and they're watching the videos and they would love to have that information. So
Okay.
other than that, I'm gonna let you guys go for today.
Okay.
And the exam is due tonight, so hopefully you guys do it. If you have any problems with that, please let me know. If you call my Google Voice number because of some sort of emergency, let me warn you that I tend not to answer phone calls from numbers that I do not recognize, and I probably don't recognize your number. So leave a message, right? It will almost certainly go to voicemail the first time, but I will absolutely get your message, and I will call you right back if it's the thing that I need to address. But be aware that if you just call and no one answers, it's not that I'm not there. It's that I think you're a spammer and I need to know the difference between a person who needs to talk to me and random spammers. All right. Have a good day. I'll see you guys tomorrow for chapter 23.